Slide 77. Okay, so the important thing in this chapter is to derive a rate law, right? Derive a rate law, and suggest a mechanism for 3 steps: adsorption, surface reaction, and desorption, right? And for adsorption, we have two choices, like the atomic adsorption and the molecular adsorption. And for the surface reaction part, we have three choices. First one is single site, and dual site, and the last one, any radial. Okay. So how to at slide 77, I would like to tell you how to observe the rate law to determine the mechanism. Okay. So in slide 77, for the special case, okay, we are two requirements. If this reaction is irreversible, and also this one is surface reaction limited. Okay, so based on these two assumptions, we can tell the mechanism from the rate law. So first one, okay, I would like to give you different surface reaction type, and we can tell something from the rate law. Okay, so first one, if that is single site. Okay, so let's tell we don't have to derive so many process. We can directly write down the rate law. Okay, so first one, if that is single site. Single site means single site, right? Single active site. Okay, so A is the reactant, B is the product. Okay, so only A adsorbed on single site of catalyst. For this kind of surface reaction, let me show you how to write down the rate law. And we can observe how to do this. Okay, you don't have to draw so many processes. We can write down directly. First, for here, it is irreversible, right? It is irreversible. So here you only see the reactant, okay? So this part, that is the reactant. You can observe your previous process and you will know the conclusion is the same. How about this part? If you remember, this part is from the site balance, right? It's from site balance, and we will get CV equals to something, right? CV equals to something like this. So this part is the same as this part, right? So this part include if this one is KAPACV if, and if this one is KBPBCV, this part should be KAPA plus KBPB, right? Remember, right? So this part include species of the soft on active site. Okay, so here you can observe here A and B are both adsorbed on the active site. So here you can write down 1 plus KAPA plus KBPB. Okay? And also you can practice if you want. You can practice to obtain the rate law. I have told you how to find this one, right? So that is the answer. We can see more for the dual site. For the dual site, if the reaction is AS plus S becomes BS plus S. Okay? I only write down the surface reaction part. So as you know, if the surface reaction is this one, the adsorption part should be this one. Okay? I don't have to mention this. You have to know this. If the surface reaction is this one, the previous step of the adsorption should be this one. Okay? And for this one, the next step is for the adsorption should be this one. Okay? Okay, I will not mention again. So let's discuss the surface reaction only. Okay, so for this part, what is the rate law? Okay, again, how about this part? This is the reactant, right? Here you should put a reactant. So the reactant is only A. So that is KPA. This K is highly possible to be KADCT if you are familiar with the previous process. Right? KAD is the rate constant for, KS is the rate constant for surface reaction, right? Ks is the rate constant for surface reaction. So if this is surface reaction limited, you will write down the surface reaction rate law as the total rate law, right? So you should use the rate constant for surface reaction. And how about CT? CT is from CV. Okay, so you can check your previous process. So this part is easy. You only have to put a reactant. How about this part? This part you should put the material or the solved on the active site, right? So here, A and B are both adsorbed. Okay? But they are the same, but they are different, right? So this one cannot be the same as this one. What is the different part? This is the single site. This is the dual site. So additionally for dual site surface reaction, that means there are 2S, right? For this kind, for 2S, you have to put this one. And I think I have derived the same process for you, right? Maybe at the slide 74. The last part in our last class, we have to do something about the dual site. And the rate law include a square here. So again, you can practice. So for this part, the adsorption equation is this one. The desorption formula is this one. So I only write down the surface reaction. So that is the answer. You can try to prove it. Okay, next. We still have another chemical reaction for dual site. How about this one? For the dual site reaction, you may have dual site becomes CS and S. Okay, if the surface reaction is like this, what is the rate law? It is easy. Okay, we do three things. First one, okay, that is a fraction, right? That is a fraction. This part, reactant, right? Reactant, so K, PA, PB. A and B are both reactants. Okay, secondly, for this part, let it include the sub species. So A, B, C are the sub on the surface, on the active site. So we got this part, okay? And another is their site. So there is a square. I recommend you to practice this one. So to practice this one, you should know the adsorption. Adsorption is right? The adsorption part, we have these two because we want to have these two. And the desorption part is also easy. That is the desorption. Okay, so the process, adsorption, surface reaction, desorption. So you can assume that is surface reaction limited and try to derive this rate law. You will find it is very easy. You can just absorb the rate law and you can know the process. Or you can observe the process. You will directly know the rate law. I still have one example for you. For the surface reaction, we have three types, right? The last type is this one, okay? You will also see this one in the final exam, okay? You will see this one in the final exam. So this part, one reactant is absorbed on the site. The other reactant is free. It's free. It's the gas form. And after reaction, okay, we got this one. So how about this one? For this one, you will know. For this one, the adsorption part is only this one, and the desorption part is this one. Okay? Okay, good. The reactant should be here. So K, PA, PB, reactant. Okay? And here, the sub species, A and the C are adsorbed on the surface. So Ka, Pa, Kc, Pc. Yeah, that's all. And that is a single site, right? Single site reaction. So you don't have to put a square here. So you can also practice this part. And we have several problems relating to this derivative for rate law in your final exam. So please be familiar with the process. Okay. So now please go to slide 84, okay? If we have time, we can go back. 84. Let's see the more important part. So that is the last part. We have to do the reactor design, reactor, like CSTR or PBR, as chapter 1, 2, 3. So how to design a reactor using the data for the catalytic reaction. So there are 4 steps, right, in slide 84. You have 4 steps. The first one, you have to observe the experimental data and derive or gauge a rate law. Okay, you gauge a rate law from the experimental data. So maybe you can see you can go to slide 86. There is a table, right? Slide 86. Can you see the table? Okay, yeah. So that is the experimental data. There are so many sets. They are 16, right? You do 16 times of the experiment, and you use different pressure for your reactant, you got a different rate law. So from this kind of table, you use the data to gauge a rate law. That is the first thing. And then secondly, this one is okay. This one is not very important to. We can see the third one first, okay? So from the rate law, you have to find the mechanism, okay? Mechanism is like what is the reaction for adsorption, surface reaction, and the desorption. That is called mechanism. So you have to know this word. If you see, please find the mechanism. That means you have to tell me what is the adsorption step, what is the surface reaction step, what is the desorption step. So other than the mechanism, you have to determine what is the rate limiting step. Okay? And then you should prove, I think this one is not listed, you should prove the mechanism fit your rate law. I will do this. I will show you this now. Okay, and the last one, we can design a reactor. Design the reactor. And actually in the design equation, if you remember, there are something in the design equation, right? 你要复习一下之前的，我会考之前的，但等下例题会有哈。So for the volume or weight of catalyst of a reactor, it is relating to molar flow rate and the conversion and the rate law. And all this thing we done here is to find the rate law. Okay, find the rate law. So this one and this one you can obtain the value from the problem, directly from the problem. The only difficult part is rate law for us. Okay, so let me show you how to do the process. So, next one. There is a reaction here. Hydrogen and toluene becomes methane and benzene. Okay, so let us use HT and MB to represent. Okay, and other information are for the initial information. So we can see this later. Let's go to the next slide. Let's see this later. Okay. So slide 86. There are 16 sets, right, of experimental data. You have to find some sets to compare by yourself and to find the relation of rate law and your species. Okay, and we can directly go to next slide. Yeah, you can read this sentence by yourself later. So let's go to slide 87. Slide 87, the first one, dependence on the product methane. Okay, so the first one we want to see the dependence of rate law on methane. That is the first one. So here, I want to use round 1 and round 2. So if you have to do the same thing as mine next week. Okay, so you will see a table, and you have to tell me what is the rounds you choose to find the relation. So here I show you, please see round 1 and the round 2. Okay, so you can go back to the table. For round 1 and the round 2, you can see PT is the same, right? PT is 1. PH2 is also 1. PB is 0. The only different part is PM, right? So set A, in set A, the first experiment show you the PM equals to 1, right? And the second experiment show you PM equals to 4. So you can see the PM increased from 1 to 4. But how about RT plan? The second column show you the RT plan, right? RT plan is 71 and 71.3. They are the same, okay? They are the same. Even if that is 0.3, because that is experiment, so you can tolerate a little bit different. So 71 and 71.3 are the same. So you will see, even if the methane increased by 4 times, minus RT are the same. Okay, so from round 1 and round 2, you can show me, you guess. This one is not related to PM. Okay, it is the first case. Yeah. And please, you have to show me around what? You have to show me the number. You cannot only say this one, you have to show, you see round 1 and round 2, and you think PM is limitedly influenced minus RT. Okay, secondly, please go to the next slide. Okay, so secondly, let's talk about the dependence on benzene. Okay. For the dependence on benzene, I want to see round 3 and round 4. For benzene, round 3 and round 4. So you have to go back to see the table again. So for set B, in set B, round 3 and round 4, you can see PT, pH2, and the PM are the same, right? You have to see the table. Okay, see your table. PT, pH2, and the PM are the same. The only different part is PB. So set B3, PB is 1. Set B4, PB is 4. Okay, so you can see when PB increase from 1 to 4, RT plan increase from 41.6 to 19.7, right? RT plan, and this one is PB that is set 4, 3 and set 4. Okay, go to the table, set 3 and set 4. You see the rate low decreased. That is different, right? Very obvious. These two are different. So decrease, but the PB increase. So you can guess this one, okay? Inversely proportional. Rate low is inversely proportional to PB. Okay, and then dependence on towing. The next slide. This one is special. So, any problem now? Okay, so this one is special. For this part, I want to use round 10, round 11, and round 14 and 15. Okay, you can go back to your table. How about round 10 and round 11? Round 10 and round 11. You got a very different RT plan, right? And PT, okay. Other pressure are the same. You have to see the table, okay. How about 14 and 15? 14 and 15, you got this one and this one. And PT is these two. Others are the same. 我等你一下，你看一下。So what is the conclusion for these two states? We have seen some similar result. I think you remember. If you can go back to okay, if you can go back to slide 35, okay? Slide 35. When we talk about the absorption isocene for the Langmuir isocene, we have seen the similar phenomena like this. Okay, can I continue? So here, we can define these two low pressure and define these two high pressure. So different results are obtained at high pressure and low pressure, right? So actually round 10 and round 11 tell you this one, right? When you increase the pressure of toluene, rate low increase as well. But for these two states, you will see is the same. They are the same, okay? They are the same. It's the same. Do Do you know the conclusion? The conclusion is so minus RT1 is proportional to like PT okay. Please remember what will be put here. Here should be 1 plus something, right? We have write down for so many times. For the rate law here, it must be 1 plus something, must. So that is the conclusion for toluene. Any problem? We still have one another species. If you have done, you can see round 7, 8, 9 to see the dependence on hydrogen. So what is the conclusion? For round 7, 8, and 9, you can see the rate law increased by twofold, right? Twofold. 72, 142, and 284. Round 7, 8, 9. And you can see pH2 increase from 1 to 2 to 4. So the conclusion is easy. If you want to write down pH2 or H2 is okay. That is just a symbol. You can determine. So we got a conclusion for 4 species, right? We have to put all the information together and to gauge the rate law. So the conclusion for the rate law, you can write down this at slide 90. Okay, now we are at slide 90. So what is the conclusion? This one, right? Equals to a fraction. It must be a fraction, okay? And here, must 1 plus something. You have to do this. For every cases, it should be a fraction. And this part should be 1 plus something for every cases. Okay? And let's see what it is at this part. Okay? So the conclusion for M, Pn will not be in the rate law, right? The first conclusion. Dependence on M, slide 87, almost no relation to Pn. And secondly, dependence on benzene. Okay, we can see this page by page. So please go to slide 88. Slide 88, dependence on benzene. B, there, yeah, you can see. Dependence on benzene. Inversely proportion, right? So for benzene, should be here. Kb, Pb. For benzene. Kb, Pb. Okay? And for toluene, Pt appeared here and here. So Kt, Pt, and also Kpt. Maybe I should use blue color if that is better for you. Once more. So last, the dependence on hydrogen here, you can see it is proportional. Okay, so that is the conclusion. So first, you will see a table. Or first, you will do experiment. You will get a several set of data. For here, you got a 16, right? 16 set of data. So you got a lot of data. You have to compare different run, like me. You choose different run, and you got a conclusion for all the species. So here we have N, B, T, H, right, or hydrogen. We have 4 species. You have to tell me the dependence on these 4 species and got one conclusion. So the species will be here or here, right? Only 2 choices, here or here. Or no relation, like a PM, no relation, so you cannot see PM here. So for the like an inverse proportion, like B, you have to write down KBPB, like this, okay? So that is the first step. You see a table and you give me this one by observing the data. That is the first part. So let's see the second part. Okay, so slide 91. The second part, okay, so you have to show me the mechanism based on this rate law. So here, there are 3 assumptions. So you can see the first one, toluene, I have shown you, right? Okay, first one, toluene. Let me write down the formula again. Okay, so that is the chemical reaction. Toluene and the hydrogen becomes methane and benzene. So the first one talk about the reactant. There are 2 reactants, right? 2 reactants, toluene and the hydrogen. And please see here, toluene and the hydrogen. So toluene and the hydrogen, they are reactant. Right? So till now, this red law is correct for this part. Okay, and how about this part? This part will show you the species adsorbed on the active site. Right? So you can see T here, but you cannot see H2 here. So that means toluene is adsorbed on the surface. You can see the sentence here. Toluene is adsorbed on the surface, but the hydrogen is in gas phase. Okay, that is the first one. So first one is for the adsorption. Okay, so second one, let's talk about the product. Let's talk about N and the B. And you can see where is N. No N here. So N is not adsorbed on the surface, but you can see B here, KBPB, so benzene is produced on the surface, or benzene is adsorbed on the active site. But you cannot see PN, right? So methane is in the gas phase. And the last one, benzene, is dissolved from the surface. Okay, so based on these 3 assumptions, let me write down the mechanism. So that is the mechanism. And also you can see the last one, around 75% heterogeneous reaction are surface reaction limited. I have mentioned this before. So first, please use surface reaction limited. Because 75% of the reaction, that belongs to surface reaction limited. Okay, so the last sentence tell you, please use surface reaction limited. to derive the mechanism. Okay, so let's write down the mechanism at the next slide. Okay, so next one, slide 92. So mechanism, you have to show me what is the mechanism for adsorption. You should give me this word, okay, this word, adsorption. So for adsorption, you can see the reactant, right? There are two reactants here, so which one or both are adsorbed on the surface? So from the conclusion, you know only toluene, right? Only toluene adsorbed on the surface. Okay? So this is the adsorption part. And for this part, it is better to write down the rate law at the same time. You know how to write the rate law, right? So RD equals to KAD. For the forward reaction, you got a PT, CV, right? PT, CV, PT, CV. For the reverse reaction, KAD equilibrium constant, and you got this one, CTS. So that is the adsorption part. Secondly, you should show me the surface reaction part. Okay, so for surface reaction, now we have T on the active site, but we only have another reactant, H2, right? So for the surface reaction, we have H or H2, okay, depending on you. And then finally we got M and the B, and you know B is adsorbed on the surface, so we have BS and M. Okay, and also maybe you can show me that it is in the gas form. Okay, and how about the rate law? How about rate law? KS, right, KS. Forward reaction, you have TS, so that is CTS, and also PH2. Okay, minus. For the reverse part, you have BS, and you have N. Right? Any problem? Last part. Desorption. Desorption is very easy. Okay? You see only one thing still adsorbed on the active site. So the desorption is to desorb the B from the active site. This part is quite easy, okay? And let me show you the rate law for desorption. RD, rate constant KD. For the forward part, concentration BS. Reverse part, PB, CV. Or, more commonly we see KB instead. KB is the adsorption equilibrium constant for B, adsorption, KB, adsorption. KD is desorption, so different. Okay, so that is the mechanism. Let's go back after 10 minutes. If you have So now, based on experimental data, we got the rate law, right? Based on rate law, we got a mechanism. The next step is to prove the rate law is correct. Is to prove. So you can write down at slide 93. So we assume that is, and also in mechanism, okay, in mechanism, please tell me which one is rate limiting. Okay, so actually this one should be mentioned in mechanism part. So in the mechanism part, you show me what is the reaction for the adsorption, surface reaction, and the desorption. Also, you have to tell me which one is rate limiting step. So based on surface reaction limited mechanism, first, let's write down the rate law for surface reaction first. So minus RT, T is toluene, right? T is toluene, the one of the reactant. So minus RT. This is the total reaction, total rate law. And the surface reaction is the limited part. So that equals to RS. Okay? And you just copy RS. You should use H or H2, just be constant. So this is the surface reaction rate law. So now you can observe which one should be modified. These two, right? CTS and CBS should be modified. So let's use the other two reactions. So we got a RD over KAD almost equals to 0, and also RD over KD almost equals to 0. Okay, and from these two reactions, we got a. You can check your previous slide. So from adsorption, we got a CTS. From desorption, we got a CBS. Okay, so you can replace the CTS and the CBS in the rate law of surface reaction. But still, there is a CV should be replaced, right? So again, let's use site balance. Site balance. So the total site CT equals to CV, CTS, CBS, right? And so you can have a CV, so that is what I mentioned. The adsorption part will be here, right? Adsorption, T and B will be here. So you got this one. Finally, you bring everything back to minus RT. Okay, you just do this by yourself, and you will get That is very similar to the rate law you observed from the data, right? Only a different part. So the last one, if you neglect the reverse reaction, okay, or you can assume it is irreversible. If you do this, you can get a same conclusion. So that is the proof. So you guess from the data, you got a correct rate law. So finally, okay, so show me the conclusion. This one should be the same. Should be the same as you obtain from the data, from the table. If you got a different conclusion, that is wrong. The mechanism will be wrong. So if you assume the mechanism but you got a different conclusion, you have to use different mechanisms. Or you have to check the process first. Okay. Before design a reactor, let's find the parameter, okay? The parameter is like a rate constant K, equilibrium constant KT, and KB. So I have told you rate law. We have to find the rate law, right? To design the reactor, to find the volume or weight of a reactor, we have to obtain rate law. So now you know the rate law is like this. But you don't know the constant, also you don't know the pressure. So we have to find the constant and the pressure. You will know the value for rate law. So now how to get a parameter? Please copy this. Please write down this one here, okay? The slide 95, where is space, right? Assuming the reaction is irreversible, the rate law for the reaction is this one. Okay, you can just put this one there. And how to find the parameter K, KT, and the KB? We use a linear relation. Okay, so at the bottom side, let's rearrange this one. So first, how to rearrange? First, I put a minus, sorry, there is a plan, always a plan. 帮我改一下，我应该一直没写，就所有的这个都有 plan 哈，所有都有 plan， 就记得。So first thing, I put a minus RT plan here, and the second part, multiply PT pH2. Okay, so let's do this. Begin from this formula, and we inverse bottom and the top side, and then we multiply PT and the pH2. We will get y over K we will get 3 parts. Okay, 3 parts. And it is like it is just like just like y equals to a0, a1, x1, a2, x2. So you rearrange the parameter and you get this linear relation. So y versus x1 and x2. Okay, so x1 here, x1 is PB, right? x2 is PT. A0, A1, A2 are the constant. You can compare. So you know K0 is, A0 is 1 over K, A1 is KB over K, right? And the A2 is KT over K, and this one is Y. Okay, and it is complicated, so we use a software, as I show you at the next slide. That is a polymass. We have seen this, right? Polymass. When we try to find the conversion at chapter 3, I think, we have seen the polymass. So I think you know how to use a polymass. You can see the polymass. 你先抄吧。OK， OK 吗 ？OK 了哈。Polymass slide 96. Okay, you see a polymass calculation. So there is a model. There's a model, and there is the variable. So you see 3 variables: K, KT, KB, right? That is the parameters we would like to obtain. So you can see the value. You can see the value. This one for K, right? And this one for KT. This one for KB. 有看到吗 ？Table polymass 的结果。So I think there is some problem in the rate law. So please modify the number. 这里写错。So at the bottom you can see 2 minus RT point, right? Minus RT point. So please modify this first. This is K. Okay, this is K. And we got a 144.76 for K, so please modify this one. Originally, that is this one, right? Originally, that is this one. Please use this one. Modify this part. And also, because this one is modified, you also modify this part. Originally, this one is this one, right? Originally, this one is this one. So please modify. Okay, so we got this conclusion. We will use this in the following example. Let me ignore 97. I will go back if I have time. 97. So please go to the slide 98, reactor design, the last part. Okay, so now the reactor design, slide 98. 如果抄完就去那吧。Okay, for the reactor design, we have 3 points. First one is place the partial pressure PT, PB, pH2 as a function of conversion. Okay, we did this in chapter 3, right? In chapter 3, so you have to convert partial pressure as function of conversion. Second one, you have to put the partial pressure in the rate law. Chapter 3. Right, we do this in chapter 3. So express this one as function of x. Express the rate law as function of x. So the last one we can use a design equation for PBR. So how about PBR? You can check your previous handout, but I can show you here. If the reactant is A, okay, if the reactant is A, RA prime equals to dFA dW. I have mentioned this before, okay? And what is A? If we want to bring conversion here, FA equals to FA0 minus FA0x. So finally you got a minus FA0 times dx over dW. That is the design equation. So please review the design equation. You can memorize this one. So you can get one conclusion about PBR. Okay? So that is the design equation for PBR. And let's see the example, the last example. Okay, so please read the problem with me, okay? There is a hydrogenation of toluene. So actually this reaction is the same as we talked about. So the reaction toluene and the hydrogen becomes benzene and methane, okay? So in this problem we talk about the same reaction. And this one is carried out in PBR. This is the first sentence. Okay, and then you can see a keyword, plot. That is the first problem. You know the meaning for plot, right? Plot, okay. So what is the target you have to plot? To plot a figure, you have to find x and y. Okay, what should be in x-axis, what should be in y-axis. So let's find out what is x and y. So you can see the second sentence. Plot the conversion. Conversion is x, right? The pressure ratio, pressure ratio and the partial pressures of toluene, hydrogen, and the benzene. So that is toluene, hydrogen, and benzene. Okay? So you can see there are 5 parameters mentioned here, and you see a keyword again as a function of. That is the keyword. And after this keyword, you see the catalyst weight. Right? So the first problem here is to draw the plot with the weight of catalyst in the x-axis, and in the y-axis you have to write down conversion pressure ratio PT, pH2, PN, no PB. Okay, so you will got 5 curves. That is the first problem. And then we have another problem. So we can follow the sentence, okay? So in the middle of the third line, the molar feed rate of toluene to the reactor is 50 mole per minute. So we got one information, FT0. Okay, and then the reactor is operated at P0, right? 40 atm. That is P0 and the T0. Okay, and then the feed consists of three things. First, toluene 30%, hydrogen. That is hydrogen 0, not H2O, okay, hydrogen 0, 45%, and the inert Yi 25%. Okay? What's more? We have the pressure drop parameter. I will tell you how to use this one later. Okay? And then the second problem, determine. You can see the keyword, determine. That is the second problem. Determine the catalyst weight. But what is the reactor? CSTR. So here, we use CSTR to do the heterogeneous reaction. That is important. And we have the bulk density. We have the bulk density like this. Okay, so that is all the information and the requirement from the problem. So we have to, first we have to plot 5 curves for the PBR. That is for the PBR. And then we have to find the catalyst weight for CSTR. So this may be the long story. So first one for PBR. You want to have something for PBR, you have to write the design equation, right? I have shown you the design equation. So let me directly use the design equation. Okay, and as I mentioned, the most difficult part is rate law. Rate law is most difficult, so please pay a lot of time on determining the rate law. Okay, so secondly, actually this one is based on the previous example, so rate law, we can directly use the rate law, okay? We don't have to find the rate law here. Let's assume we have the rate law. So this rate law is from the previous problem, okay? And also we know the value for the constant. I have shown you how to calculate the constant by polymass, right, previously. Constant you can obtain by polymass. But when you take the exam, you cannot use computer. So I will give you the constant directly. So please write down the constant. That is K, and also we have KB, we have KT, okay? Please directly use the value here. So now, what is remained? Pressure, right? We want to find we want to draw the plot, so we use this formula. And in this formula, we want to find the rate law. Okay, so you see rate law here. And I have given you all the value for constant. So now you have to write down pH2, PT, and the PB. That is the logic. So then, that is stoichiometry. Okay, so now we use pressure everywhere, right? So PT, you use the ideal gas law, P equals to CRT, right? And previously, we know what is CT. CT0 times 1 minus x, 1 plus epsilon x. Don't forget this thing. If the volume could change, right? So if the volume is not constant, you should use 1 plus epsilon x here. And the T, you have to check the equation. Okay, so the conversion, x is the conversion for t, so here 1 minus x. You have to review in the previous chapters, okay? And then we combine them, and we got pt equals to pt0. Okay, so that is the first thing. And the one thing I want to show you is the pressure drop. Pressure drop is mentioned in chapter 4, but we don't have time in chapter 4. So if there is pressure drop, please multiply y here. It is the pressure drop ratio.如果我们今天没有讲完，我下礼拜就要上课，礼拜二。 and then let's find some unknowns. First, I would like to find the epsilon. Do you remember what is epsilon? Epsilon YT0 times delta. 要复习哦，之前的 YT0 times delta, right? What is YT0? Taurine, 30%. You can see from the problem. So YT0, 30%. What is delta? Delta is the coefficient, right? Coefficient. So for the product, the coefficient is positive. For the reactant, the coefficient is negative. Okay, so here epsilon equals to 0. There is no volume change. Because epsilon equals to 0, so we know this one. Okay, that is PT. How about pH2? We want the pressure, right? pH2 equals to PT0 theta H2 minus XY. You remember, right? And you can bring theta 2. What is theta 2? Theta 2 could be YH20 over YT0. So that is 0.45 over 0.3. Therefore, PT equals to pH2 equals to this one. We still have one pressure, PB, right? The same PB, PT0, theta B plus XY. And you know theta B is 0 because initially there is no benzene. Okay. Theta B, YB0, YT0. 我等你了。We got all the pressure. We got all the pressure. 我只等你10秒哎，应该没关系吧？ So now what's next? How about Y? You don't know Y, right? What is the pressure drop ratio? So what is the ratio of P and P0? P0 is the initial pressure, and it equals to this one. Okay, alpha is the constant provided in the example. W is the weight of catalyst. So alpha. You have alpha from the problem. So that is Y. What is the unknowns? Let's check. So I want the PT, pH2, and the PB, right? And I have mentioned I want them to be the function of X, right? Function of X. So here, X is okay to be here. Y here, right? Y here. The only remaining thing is PT0. Okay, so now let's find the PT0. Do you know PT0? It is easy because the total pressure. P0 is the total pressure. You times the initial ratio. Okay, so total pressure 40 atm. Initial ratio for towing is 30%. So this is PT0. We will use polymass. This part. Okay, so now you got the pressure as a function of conversion.我写什么？休息一下，看来还是抄不完。抄完了哈，抄完了。Okay, and we have to plot, right? Now we have to plot. But before plotting, we have to find the range for W. Find the range for W. So here, we know the entering pressure is 40 atm, right? There's a tube. PBR. PBR. And we know P0 is 40 atm. So initially the pressure is 40 atm. So what would be the final pressure if this one can react very smoothly? So let me tell you, the final pressure, it is better to use exit 出口 should be larger than 1 atm. Larger than 1 atm, because in the word, that is 1 atm, right? That is 1 atm. So the exit pressure should be larger or should be 1 atm. The gas can come out. If the pressure is smaller than 1 atm, the gas cannot come out because in the environment, the pressure is almost 1 atm. So we assume exit pressure is 1 atm, and we know the entering pressure is 40 atm. So this is P0. This is P. Okay, we bring the value later. We bring the value, and we got 1/40. Okay? So the purpose is to find the weight of catalyst. Okay, so that means if you put around 10,000 kilogram, if you put around 10,000 kilogram catalyst inside, the exit pressure will be 1 atm. So let's draw the plot. 快要结束了，你懂吗？
我现在要看的是。
好，so 总共102页啊，去102页，好累啊，抱歉，我也觉得好累。102页 ，you see the polymass, right? You see the polymass and the differential equation at the top, dx over dw equals to 那什么是 minus RT over FT0, right? You see the differential equation, and also you see the parameter. They are 14 parameters. So you put everything in the software. You can get a curve at a slide 103. Okay, so you can get a slide. you can get figures. So the first figure is xy versus w. The second figure is pressure versus w. Okay? And there are some sentences at the bottom so you can see how to read this problem, this figure. But the more important thing is the CSTR catalyst. 让我把最后一部分讲完。So the second part is to find the weight of catalyst in CSTR. Alright, so for CSTR, again, please go back to review 104. You can write down it at 104. So previously for CSTR, we have FT0 in minus out plus generation. Previously, we have this one, plus generation equals to the accumulation. I forgot, chapter 2. But here, I want to modify this term as RT1 times W. Okay, that is the only thing we should modify. So you can rearrange and obtain this one, okay? For CSTR, heterogeneous reaction. Yeah. FT is FT0 minus FT0x. I have told you before, so we got this one. This is the design equation for CSTR. So we want this one we have these two in the problem, so now we want the minus RT plan. Okay, so please bring everything. I think you have all the value. Please calculate by yourself. You have minus RT plan, right? I have shown you. So in minus RT plan, we have constant K, KB, KT. I have given you the value. Also, we have pressure of toluene, hydrogen, and the benzene, right? And we have write down the pressure. So please put all the values inside. You will get this value. Please calculate by yourself. So the last part, bring everything. Okay, here, bring everything. You will get 50 mole per minute and conversion, and also rate low. Okay, and you can find it is equal to this one. And don't forget, we need a volume, okay? So the volume equals to the weight over density. So that is the volume.我来用中文讲一下结论。下礼拜的考试呢，只有3题。我最近想做3次，所以跟你多说一点。只有3题，基本上都精教的，你也发现前面没什么好考的嘞，所以我前面都不用背的部分就不用背，它基本上全部都是计算。那会有一题就是它会指定不同的速率决定步骤。可能是 adsorption， 可能是 surface reaction， 可能是 desorption， 我会指定给你，不用乱猜。然后我会给你一排就是反应式，所以你要用那些反应式 用我指定的输入决定步骤把 rate load 导出来。好，那 constant 我是有很多种写法，一下 k、b、k、a、d、k 什么，你就用一致的写法，你要一致。好，所以你在，我跟你说，你在这个，因为我都跟你说要考什么，所以你要写的标准，好吧？所以我要抓的比较严。你在写 reaction， 我刚刚没写 ，sorry， 但你要写。你在写 reaction 的时候，你要告诉我正反应 constant 跟逆反应 rate constant， 就整个是完全对的给我。然后你在写rate load 的时候，一堆东西你要写对的，就这整个逻辑是全部要符合前面，你不要 K 乱写。好，那到最后反正 K 要一致，那你用什么 K 我不 care， 但你 K 要一致。那第二个部分呢，我讲那个 table， 我会给你一组 table。可能有好几行，然后你要从 table， 就我刚刚做的整个 process， 你要从 table 观察出 rate load 会长什么样，这第一部分。第二部分你就要从那个 rate load 把 mechanism 告诉我 ，mechanism 就是吸附、表面反应跟托付会是什么，对不对？那你写了 equation， 你写了方程式之后，你要把 rate load 也写在旁边，然后告诉我谁是输入决定步骤。那没有说过，如果我没告诉你，你要猜，你就先猜表面反应。好，你不要也可以，如果你时间很多，但我建议你可以猜表面反应。然后是什么啊？然后你要证明，再来就是你要证明，我们最前面教的，你要证明你猜的 rate load 是对的，好吗？最后一部分就是这里。就是要你算这个，可能是催化剂的重量，可能是体积，我有点忘记。好，就是他告诉你是 CST 所以请你回去，我已经告诉你回去把 CST 读一下，就是至少 design equation 你要会，然后它的重点就会是负 RT， 就是这个 rate load 要怎么写出来。好，衷心希望没有人被我当掉，好不好？所以我已经讲这么多了。好，你还是0分，我可能就会思考一下你到底在干嘛。OK， 有问题再来问我。